In this video, we're going to talk about summation notation. This is a concise way to represent the addends in sums for which the addends follow a pattern. Let's take a look at summation notation for the sum of the first 20 positive integers. This symbol is the Greek letter sigma, and it represents sum. In other words, the symbol is telling us to take the sum of the first 20 positive integers, where I is our index of summation, that indicates our lower limit of summation. In other words, the number that we need to begin adding with. And at the top of sigma, we have our upper limit of summation, which indicates the last number that we should add to our sum. The symbol I that follows sigma represents each addend, and it tells us the pattern that we're going to use for the summation. If we were to expand the summation, it would be the sum of the first 20 positive integers. So in other words, we would simply add all integers from 1 to 20. And in this case, our sum is 210. Sometimes we're given a summation for which the upper limit of summation is infinity. So here again, we have our index of summation telling us to start at the number 1, where this formula represents each addend, and our upper limit of summation is infinity. Now, of course, we aren't able to write every number from 1 to infinity, since we would never be able to stop. So we start our expansion by writing the first few terms and then adding ellipses to indicate its continuation. So we would have, beginning at 1, 1 times 1 plus 1 over 2, where we substituted 1 for n, plus 2 times 2 plus 1 over 2, plus 3 times 3 plus 1 over 2, plus, and then our ellipses to indicate the continuation of the sequence to infinity. Of course, we could simplify the formula so that our sequence would read 1 plus 3 plus 6 plus ellipses. Incidentally, the formula for a triangular number is n times n plus 1 over 2. And this is a formula that you'll see quite often when working with sums. Now sometimes we are given a series and asked to represent it using summation notation. In this case, starting with n equals 1, let's write the series using summation notation, where we have 2 minus 4 plus 6 minus 8 plus 10. What we need to do is try to determine a relationship between n and the terms in our summation. Sometimes this can be quite challenging, and it may require some trial and error until you gain more practice working with summations. In this series, we can see that each subsequent digit is double the one before and is of the opposite sign. So we have 2 minus 4 plus 6 minus 8 and so on. So I might start out using negative 1 to the power of n. Now let's take a look at it. If we use negative 1 to the power of n, and start with n equals 1, then we would have negative 1 plus 2, plus positive 1. And when n equals 3, we'd have negative 1 again. So we can see pretty clearly that this isn't going to work, because it doesn't match this series. Since each successive term doubles, we know that we must have 2 times n somewhere in our summation formula. So we can try 2n to the negative 1 to the n, and when n equals 1, that would give us 2 times negative 1, times positive 1 times negative 1 to the power of 1, which equals negative 2. And when n equals 2, we would have positive 4. Again, this one doesn't quite work, because although our values are doubling and appear to match so far, the signs are opposite the original series. So I know that this one will also not work. However, if we take negative 1 to the n times 2n and multiply that by negative 1, then we get something that looks like it will work. So let's try it. Negative 1 times negative 1 to the power of 1 times 2 times 1 equals positive 2. Negative 1 times negative 1 squared times 2 times 2 in place of n gives us negative 4. We could continue plugging in values for n, and we would find that this formula works for the series. That is, negative 1 times negative 1 to the n times 2n. Now what we'll do is clean this up just a little bit I know that when I multiply like bases, I can add my exponents. So I have negative 1 to the first times negative 1 to the n. And I'd also consider whether or not I wanted to rearrange the order of my factors in this expression. So you might choose to write this as 2n times negative 1 to the n plus 1, coming from when we multiply our like bases and add our exponents. Or you could say negative 1 to the power of n plus 1 times 2n. Putting this into our summation formula, we have the sum from n equals 1 to 5. And the reason this goes to 5 is because this is the value that, when plugged into the formula, will yield 10. So anyway, the sum from 1 to 5 of negative 1 to the n plus 1 times 2n. So this concludes our example on just a few basics regarding summation notation. I hope you found it helpful, and we'll see you next time.